Before there was light, before there was matter, before time could be measured in any meaningful way, the universe did not exist in a state that can be accurately described as empty. Not darkness, not silence, not absence. Modern physics increasingly suggests that what we intuitively call nothing is not a physically valid condition. The most disruptive idea in contemporary cosmology is not that the universe had a beginning. It is that the concept of absolute nothingness may never have existed within physical reality at all. For most of human history, nothing was treated as the default state of existence, a baseline from which everything else emerged. Philosophy framed it as absence. Classical physics treated it as an inert background. Everyday intuition assumes it is simple and passive. Over the last century, that assumption has been systematically invalidated. Advances in relativity and quantum physics show that regions defined as empty still possess measurable properties. They exhibit structure, constraints, and energy behavior that cannot be eliminated, even in principle. If emptiness itself obeys physical rules, then the origin of the universe does not require violation of those rules. It requires understanding them correctly. This video examines how science redefined nothing, why classical intuition fails under experimental scrutiny, and what modern physics implies about the conditions that preceded the earliest observable moments of the universe, if the concept of before remains applicable at all. The central thesis of this video is simple, but deeply counterintuitive. The universe did not emerge from nothing, as that word is commonly understood. Instead, what we call nothing is a physical system governed by laws, fluctuations, and geometric constraints. And those properties may make the existence of something not only possible but unavoidable. Understanding this requires abandoning everyday intuition about space, time, and emptiness. It requires tracing how philosophy, classical mechanics, relativity, and quantum physics each redefined what nothing means, and how each definition quietly invalidated the one before it. By the end of this analysis, you will understand why the question, "Why is there something rather than nothing?" may be improperly framed, and why a more precise question is whether absolute nothingness could ever exist at all. Long before equations, detectors, or telescopes, the idea of nothing functioned as a boundary problem in philosophy. It marked the limit of what could be coherently described, rather than a concrete state of reality. Ancient Greek philosophers approached nothingness with caution. Aristotle, in particular, rejected the possibility of a true vacuum outright. His reasoning was not based on observation, but on logical consistency. If nothing were to exist, it would have to possess definable characteristics. If it possessed characteristics, it would no longer qualify as nothing. From this perspective, absolute emptiness created contradictions. Motion, causality, and change all appeared to require a medium through which they could occur. Without such a medium, fundamental features of reality became impossible to explain. This reasoning led Aristotle to conclude that absolute emptiness could not exist. The idea later condensed into the phrase, "Nature abhors a vacuum," a view that dominated Western thought for nearly 2,000 years. Crucially, Aristotle's position was not rooted in superstition or mysticism. It was an attempt to preserve logical coherence, a universe that allowed true nothingness, introduced paradoxes that could not be resolved using the conceptual tools available at the time. As philosophical inquiry progressed into the early modern period, the problem of nothingness was reformulated with greater precision. This shift is most clearly associated with the work of Gottfried Wilhelm Leibniz. Leibniz reframed the issue as a foundational, explanatory demand. Why does anything exist at all, rather than nothing? This was not a scientific question in the contemporary sense. It was an attempt to extend causal reasoning to its absolute limit. Central to Leibniz's argument was the principle of sufficient reason, the idea that nothing occurs without an explanation. From this perspective, nothing appeared simpler than something, and therefore did not require justification. The existence of the universe, by contrast, did. This reasoning established a lasting intuition that nothingness is the natural baseline of reality, and that existence represents a deviation from it. That assumption continues to shape how questions about cosmic origins are framed. Modern physics will ultimately reverse this intuition. Instead of treating nothingness as the default state, it will reveal it as a concept that lacks physical stability or operational meaning. The nature of nothingness shifted from abstract speculation to empirical investigation when emptiness became experimentally accessible. In the 17th century, Evangelista Torricelli demonstrated that air possesses weight and exerts pressure. Using a mercury-filled glass tube, he showed that a column of mercury would fall and stabilize at a specific height, leaving a region above it that contained no air. This region appeared to be empty. The result marked a critical transition. The vacuum was no longer treated solely as a philosophical impossibility. It became a physical condition that could be created, measured, and studied. Yet even these early vacuums were not truly empty. Trace gases remained. Thermal radiation persisted. Electromagnetic effects were unavoidable. What Torricelli demonstrated was not the existence of nothing, but the removal of air as a medium. Despite these limitations, the experiment fundamentally reframed the debate. The central question shifted from whether nothingness could exist to how closely physical systems could approach an absence of matter. That shift from existence to degree would later prove essential. It opened the door to increasingly precise definitions of emptiness, and ultimately to the realization that complete emptiness may be unattainable, even in principle. By this point in the analysis, the idea of emergence from nothing has been effectively replaced. Across multiple layers of theory and observation, the earliest describable state of the universe is no longer treated as emptiness or absence. It is described as a dynamic configuration of quantum fields, space-time geometry, and energy, each governed by well-defined, if incomplete, physical laws. Vacuum energy, instability, inflation, symmetry breaking, dark matter, and dark energy do not represent separate explanations. Together, they form a coherent picture in which structure arises naturally from physical conditions rather than from an absence of them. This reframing shifts the core question of cosmic origins. The problem is no longer how something emerged from nothing. It is whether the rules that permit such a universe could have been otherwise, or whether they represent unavoidable features of physical reality. At this stage, cosmology reaches the limit of what current theory can resolve. The mechanisms that shape the observable universe are increasingly well constrained. What remains uncertain is not their operation, but their ultimate origin. That uncertainty does not signal failure. It marks the boundary between what is currently explainable and what remains open, setting the stage for deeper questions about time, causality, and the limits of physical explanation. The unresolved tension surrounding vacuum energy highlights a deeper pattern that runs through modern cosmology. Phenomena traditionally associated with the smallest scales of physics appear to influence the largest structures in the universe. The same quantum principles that govern subatomic fields also shape the initial conditions from which cosmic structure evolves. At microscopic scales, quantum fluctuations introduce unavoidable variations in energy and field values. During the early universe, these variations do not remain confined to the quantum domain. Under the influence of gravity, they are amplified, stretched, and preserved across expanding space-time. This process links the behavior of quantum fields to the distribution of matter and energy on cosmic scales. Small differences in initial conditions become large-scale density variations. Over time, gravity enhances these variations, allowing structure to emerge. The result is a continuous chain of influence. Quantum effects establish initial conditions. Gravitational dynamics amplify them, and observable structure follows. No sharp boundary separates these stages. They represent different regimes of the same underlying physical framework. This continuity challenges the traditional division between particle physics and cosmology. Rather than addressing separate domains, both disciplines describe different scales of the same system. Understanding the universe therefore requires models that remain coherent across many orders of magnitude. The macro-scale behavior of the universe cannot be fully understood without reference to microscale physics. Likewise, the consequences of quantum behavior extend far beyond the subatomic realm, shaping the evolution of space-time itself. If dark matter is required to explain how structure forms and holds together, observations of cosmic expansion reveal a second, very different discrepancy. Measurements of distant supernovae, combined with data from the cosmic microwave background and large-scale structure, show that the expansion of the universe is not slowing down. It is accelerating. Under classical expectations, gravity should gradually reduce the expansion rate. The observed acceleration therefore implies the presence of a pervasive energy component that counteracts gravitational attraction. This component is known as dark energy. Dark energy does not cluster like matter. It does not form structures. Instead, it acts uniformly across space, exerting a form of negative pressure that drives accelerated expansion. Its effects become dominant only on the largest scales, where matter becomes sufficiently diluted. In its simplest interpretation, dark energy behaves like vacuum energy predicted by quantum field theory, an energy intrinsic to empty space itself. In general relativity, such energy naturally influences the geometry and expansion of space-time. However, this apparent connection introduces a severe problem. Quantum field theory predicts vacuum energy values vastly larger than what is inferred from cosmic acceleration. The observed magnitude of dark energy is extraordinarily small by comparison. This discrepancy, known as the cosmological constant problem, represents one of the deepest unresolved issues in modern physics. It signals a fundamental mismatch between quantum theory and gravity, and highlights how little is still understood about the physical properties of empty space. Dark matter explains how structure forms. Dark energy explains how the universe expands. Together, they reinforce a central theme of modern cosmology. The large-scale behavior of the universe is dominated not by what is directly visible, but by components inferred through their gravitational and geometric effects. The observational record does more than confirm early universe models. It also exposes a persistent discrepancy. When the distribution of matter inferred from relic signals, such as the cosmic microwave background and baryon acoustic oscillations, is evolved forward using known physical laws, the resulting universe does not match what is observed unless an additional component is included. This mismatch appears repeatedly across independent measurements and vastly different scales. Observations of galaxy rotation curves show that stars orbit far faster than visible matter alone can account for. Gravitational lensing reveals more mass-bending light than can be traced to luminous sources. On the largest scales, the growth of cosmic structure proceeds too efficiently to be driven by ordinary matter alone. These results point to the presence of matter that does not emit, absorb, or reflect electromagnetic radiation. This component, known as dark matter, interacts primarily through gravity. It does not announce itself through light, but through its influence on motion, clustering, and structure formation. Its existence is inferred not from direct detection, but from consistent gravitational effects that visible matter cannot explain. Dark matter plays a central role in cosmology. It provides the gravitational framework within which galaxies and clusters form. Ordinary matter follows its distribution, accumulating in regions where dark matter density is highest. The conclusion is not optional. If the observational fossils described earlier are taken seriously, dark matter is not an exotic addition. It is a necessary component of the universe as it is observed. The early universe cannot be observed directly. Its initial conditions are long gone, and the processes that shaped them occurred far beyond the reach of any experiment. Yet cosmology is not built on speculation. Instead, it relies on relic signals, physical patterns that preserve information about early conditions and persist across cosmic time. These remnants allow theoretical models to be tested against observation, transforming abstract scenarios into falsifiable explanations. Two such signals play a central role. The most direct record of the early universe is the cosmic microwave background. It appears as a nearly uniform radiation field observed in every direction. This radiation originates from the moment when the universe became transparent, allowing light to travel freely through space for the first time. What is observed today is not a view of objects, but a record of conditions. Tiny temperature variations across the CMB encode information about early density differences, space-time geometry, and the expansion rate of the universe. These variations follow precise statistical patterns predicted by cosmological models that incorporate inflation and vacuum-driven dynamics. Over the past several decades, the CMB has been mapped with increasing accuracy by missions such as COBE, WMAP, and Planck. Each successive survey has reduced uncertainty and tightened constraints on fundamental parameters. The result is a quantitative snapshot of the universe at a well-defined stage, providing a direct test of early universe physics. The same early conditions that shaped the cosmic microwave background also left lasting imprints in the distribution of matter. Before atoms formed, pressure-driven density waves propagated through the hot plasma of the early universe. When radiation decoupled from matter, these oscillations ceased, fixing a characteristic length scale into the distribution of matter. As structures formed over billions of years, this scale became embedded in the spatial arrangement of galaxies. These features, known as baryon acoustic oscillations, act as a standard ruler for measuring cosmic expansion. By comparing this scale across different epochs, cosmologists reconstruct how the expansion rate of the universe has changed over time. When combined, the cosmic microwave background and baryon acoustic oscillations provide independent lines of evidence. Each probes different physical processes and eras, yet both converge on the same cosmological history. Their agreement is not stylistic. It is empirical. And it is this convergence that allows cosmology to move from narrative to measurement, the processes described by vacuum instability and inflation operate far beyond direct intuition. To make sense of them, cosmology relies on a structured timeline. This timeline is not organized around familiar units of time, but around energy scales and physical regimes. Each stage marks a point at which different laws dominate and different forms of behavior become possible. Only by anchoring abstract mechanisms to this sequence can the universe's early evolution be meaningfully described. When the universe is traced backward toward its earliest moments, the first meaningful boundary appears at the Planck time, approximately 10 to 43 seconds after extrapolation from the present. At this scale, energies become so extreme that quantum effects of gravity can no longer be ignored. General relativity and quantum mechanics, both highly successful in their respective domains, cease to function reliably when applied together. Crucially, this moment does not represent a physical event. It marks a limit of description. Existing theories no longer produce testable or consistent predictions beyond this boundary. The Planck epoch, therefore, defines not the beginning of the universe, but the point at which known physical frameworks stop being sufficient. As the universe expands and cools beyond this boundary, it enters regimes where distinct physical laws begin to emerge. At sufficiently high energies, the fundamental forces are believed to have been unified into a single interaction. As conditions change, this symmetry does not persist. Instead, it breaks. This process, known as symmetry breaking, alters how particles behave and allows the forces of nature to differentiate into the forms observed today. Interactions that were once indistinguishable acquire distinct properties and strengths. Symmetry breaking is not unique to cosmology. It is a recurring principle throughout physics. Systems governed by high-energy conditions often exhibit simpler, more unified behavior, while lower-energy systems display greater complexity and differentiation. In the early universe, symmetry breaking provides the mechanism by which diversity emerges from uniformity. As expansion continues, the universe eventually cools to a point where another critical transition occurs. Hundreds of thousands of years after the earliest describable moments, electrons combine with atomic nuclei to form neutral atoms. Prior to this, free electrons scattered photons efficiently, preventing light from traveling long distances. Once neutral atoms form, this scattering sharply decreases. Radiation decouples from matter. and light is able to propagate freely through space. The radiation released at this moment remains observable today as the cosmic microwave background. It provides a direct record of the universe at the point when it first became transparent. This transition anchors cosmological theory in observation. The abstract processes described by inflation, vacuum instability, and symmetry breaking leave behind a measurable signal that persists across cosmic time. When vacuum instability is applied to the earliest stages of the universe, its consequences are no longer microscopic. Under extreme conditions, the behavior of vacuum energy is capable of reshaping space-time itself. The theory of cosmic inflation emerges from this realization, not as an abstract hypothesis, but as a mechanism that connects quantum instability to large-scale cosmic structure. Inflation describes how a high-energy vacuum state can drive a brief but transformative phase in the universe's evolution. The motivation for inflation did not arise from philosophical preference, but from concrete observational problems that classical cosmology could not resolve. One such problem is the horizon problem. Regions of the universe separated by vast distances exhibit nearly identical physical properties, even though standard expansion models suggest they were never in causal contact. Without a mechanism for early interaction, this uniformity remains unexplained. A second issue is the flatness problem. Observations show that the geometry of space-time is remarkably close to flat. In classical cosmology, such a condition would require extremely fine-tuned initial parameters, with no clear justification. A third concern involves the absence of certain relics predicted by high-energy physics, such as magnetic monopolies. Standard models suggest these objects should be abundant, yet they are not observed. Inflation offers a single mechanism that addresses all three problems simultaneously. By rapidly expanding space-time early on, it allows distant regions to share common initial conditions, drives the geometry toward flatness, and dilutes unwanted relics to undetectable levels. The key to inflation lies in how vacuum energy behaves. Unlike matter or radiation, vacuum energy does not dilute as space expands. Its energy density remains nearly constant. As space-time grows, the total vacuum energy contained within it increases rather than disperses. This property leads to exponential expansion. As long as the universe remains in a high-energy vacuum state, expansion accelerates instead of slowing down. During this phase, quantum fluctuations inherent in the vacuum are stretched from microscopic scales to macroscopic ones. What begin as small variations in field values become differences in energy density across space. These amplified fluctuations serve as the initial conditions for all later structure. Galaxies, clusters, and large-scale cosmic patterns trace their origins back to variations seeded during inflation. Although inflation occurs far beyond direct experimental access, its consequences leave measurable imprints. The most significant evidence comes from observations of the cosmic microwave background. This radiation preserves a snapshot of the universe when it first became transparent to light. Tiny temperature variations across the sky follow precise statistical patterns predicted by inflationary models. These patterns reflect the distribution of primordial fluctuations generated during the inflationary phase and later imprinted onto space-time. While inflation remains a theoretical framework rather than a directly observed event, its predictions align closely with the structure of the observable universe. Taken together, vacuum instability and inflation form a continuous narrative. Quantum fields and unstable high-energy states drive transitions that shape space-time itself. What appears, from a classical perspective, as an extreme and unintuitive episode follows directly from the behavior of vacuum energy under quantum rules. Once vacuum energy is understood as unavoidable, a second, more counterintuitive consequence follows. Vacuum states are not necessarily stable. In quantum field theory, a vacuum is not defined as nothing, but as the lowest energy configuration available under a specific set of conditions. Crucially, those conditions are not fixed. When they change, the vacuum state itself can change. A vacuum that is stable under one set of conditions may become unstable under another, allowing the system to transition to a lower energy configuration. This process is known as vacuum decay. Instability, in this context, is not a flaw in the theory. It is a built-in feature of how quantum fields behave. To understand how vacuum decay becomes physically relevant, physicists distinguish between different types of vacuum states. A false vacuum is a metastable configuration. It appears stable under small disturbances, but it is not the lowest possible energy state available to the system. Given sufficient fluctuation or a change in conditions, it can transition to a more stable vacuum. In early universe cosmology, it is hypothesized that the universe occupied such a false vacuum shortly after its earliest describable moments. When this vacuum decayed, it released energy and altered the behavior of space-time itself. This idea does not rely on exotic assumptions. Phase transitions are a standard feature of physics. Systems routinely shift from one state to another when underlying conditions change. What distinguishes the early universe is not the mechanism, but the scale and consequences of the transition. The importance of vacuum instability becomes clear when considering the alternative. If the early universe had occupied a perfectly stable vacuum, one with no lower energy state available, no transition would have occurred. Without transition, there would have been no large-scale change, no expansion driven by vacuum energy, no differentiation of forces, no emergence of structure. Instability allows transitions. Transitions allow variation. Variation allows complexity. From this perspective, the emergence of a dynamic universe does not require an external trigger or special intervention. It follows directly from the behavior of quantum fields under extreme conditions. What appears from a classical viewpoint as a precarious or unlikely situation is, in quantum theory, a natural outcome. The early universe evolves not in spite of instability, but because of it. At the center of modern cosmology lies a concept that directly contradicts everyday intuition and classical physics: vacuum energy. In quantum field theory, particles are not fundamental objects placed into space. Each particle corresponds to an underlying field that exists everywhere in space at all times. What changes is not the presence of the field, but its excitation. When particles are absent, the field does not disappear. It settles into its lowest possible energy configuration, known as the vacuum state. This immediately raises a critical question. If the vacuum represents the lowest possible energy state, why does it not contain zero energy? The answer comes from a fundamental constraint built into quantum mechanics itself. Quantum theory limits how precisely certain physical quantities can be defined at the same time. One such limitation applies to energy and time. Because of this constraint, a system cannot remain in a state of perfectly fixed energy over any finite duration. Absolute zero energy would imply complete stability, which quantum mechanics does not permit. As a result, even the lowest energy state allowed by the theory retains residual activity. Quantum fields cannot be perfectly still. Their values fluctuate, and these fluctuations carry energy. This residual energy is known as zero-point energy. This conclusion does not depend on interpretation or philosophical preference. It follows directly from the mathematical structure of quantum mechanics. Once quantum fields are accepted as fundamental, zero-point energy becomes unavoidable. If zero-point energy is unavoidable, the next question is whether it produces observable effects or remains a purely theoretical artifact. It does produce observable effects. One of the clearest demonstrations is the Casimir effect. When two uncharged, conductive plates are placed extremely close together in a vacuum, they experience a measurable attractive force. No electric charge is involved. No classical force is applied. The force arises because the plates impose boundary conditions on the quantum fields. Only certain field modes are allowed to exist between the plates, while a broader range of modes remains possible outside them. This difference alters the vacuum energy density on either side, producing a net force. The Casimir effect shows that zero-point energy is not an abstract bookkeeping device. It has measurable mechanical consequences. Empty space responds to constraints, and that response can be detected experimentally. Once vacuum energy is established as physically real and experimentally measurable, its relevance to cosmology becomes unavoidable. In general relativity, energy and mass are sources of space-time curvature. Any form of energy that exists throughout space contributes to how space-time behaves. Vacuum energy, by definition, is present everywhere. This creates a direct link between quantum-scale physics and the large-scale structure of the universe. The expansion, geometry, and evolution of space-time cannot be determined solely by matter and radiation. The properties of space itself must also be taken into account. The implication is fundamental. The universe is shaped not only by what occupies space, but by the physical state of space itself. Understanding cosmic origins, therefore, requires understanding vacuum energy, not as an exotic addition, but as a built-in feature of physical law. This historical progression is not incidental. It reveals a consistent pattern in how deeper levels of analysis reshape fundamental concepts. Each time science has attempted to define nothing with greater precision, that definition has failed. What appears empty under one framework reveals structure, constraints, or dynamics under another. Increasing explanatory power has never preserved absolute emptiness. It has consistently replaced it. This pattern is essential for understanding cosmic origins. The state preceding the earliest observable moments of the universe, if such a state can be meaningfully defined, was not philosophical absence, classical void, or inert vacuum. It was a physical condition governed by rules that remain only partially understood. Recognizing this reframes the Big Bang itself. It is not the creation of the universe from nothing. It is a transition between physical regimes, marking the limit of current descriptions rather than the beginning of existence. With this context established, the focus can now shift from historical definitions to mechanisms. How known physical laws operate under extreme conditions, and how they give rise to the universe we observe. Quantum theory completed the breakdown of classical emptiness. In quantum field theory, space is not an empty backdrop populated by particles. Every region of space is permeated by quantum fields that exist independently of whether particles are present. What is commonly called a vacuum is not an absence of these fields, but their lowest possible energy configuration. Even in this minimum energy state, quantum fluctuations persist. Energy cannot remain perfectly fixed. Field values cannot remain perfectly static. As a result, measurable activity remains unavoidable. These effects are not theoretical abstractions. They are confirmed experimentally. One of the most direct demonstrations is the Casimir effect, in which two uncharged, closely spaced conductive plates experience an attractive force due to differences in the allowed quantum field modes between and outside the plates. No classical force is involved. From a quantum perspective, empty space is a physical system with defined properties, governed by mathematical laws and capable of producing observable consequences. At this point, nothing no longer exists in any operational or experimental sense. Every physically definable state retard. Albert Einstein's general theory of relativity introduced a fundamental revision of what space is and how it behaves. In this framework, space is no longer a passive container in which events occur. It is part of a unified space-time whose geometric structure responds directly to mass and energy. Time and space are inseparable, and gravity is no longer treated as a force acting across a distance, but as a manifestation of space-time curvature. This shift eliminated the Newtonian notion of empty, inert space. Even in the absence of matter, space-time retains geometric properties that influence motion and the propagation of light. Its structure can change, evolve, and transmit gravitational effects. As a result, empty space in relativity is not truly empty. It is a physical entity with measurable properties, defined by geometry rather than by material content. This marked the first decisive break from the classical idea of nothingness. Space could no longer be treated as a neutral background. It became an active component of physical reality, governed by the same laws as matter and energy. Isaac Newton introduced a decisive conceptual shift in the treatment of space. He proposed the existence of absolute space, a fixed, immutable framework within which matter moved and forces acted. In Newtonian physics, empty space possessed no dynamics of its own. It did not change, respond, or evolve. It existed independently of matter and was unaffected by the events occurring within it. Objects moved through space, and forces acted across it, but space itself played no active role. This marked the first widely accepted scientific model in which a form of nothing was not only permitted, but essential. Absolute space functioned as a necessary background that enabled motion, inertia, and universal laws to be defined. However, this conception carried a hidden cost. If space existed independently of matter, then its existence itself demanded explanation. Why did absolute space exist at all? Why did it possess a specific structure rather than another? And what sustained its uniformity? Newton was aware of these unresolved questions. Although his framework proved extraordinarily successful in practice, it left the ontological status of space unexplained, a tension that would persist until the foundations of physics were reconsidered in the 20th century. The unresolved problem is not why the universe exists, but why the laws governing it take the specific form they do. Modern cosmology increasingly constrains how the universe behaves under known laws, yet it does not explain why those laws exist, or why their parameters fall within the narrow ranges that permit the universe observed today. this question sits at the boundary between physics and philosophy. It is possible that future theories will reframe the problem, reduce it to deeper principles, or show that certain features of physical law are not contingent at all. It is also possible that some aspects of this question lie permanently outside the scope of empirical investigation. What modern cosmology establishes with clarity is more limited but decisive. Whatever the ultimate explanation of physical law may be, it does not begin with absolute nothingness. The frontier of inquiry lies not in the absence of reality, but in the structure of the rules that govern it. The question, why is there something rather than nothing, persists because it feels natural. In everyday experience, absence appears simpler than presence. Empty rooms, silence, and inactivity seem easier to imagine than complex systems. Human reasoning, therefore, treats nothingness as a baseline state and existence as something that requires explanation. This intuition is compelling, but it is not a guide to fundamental physics. What feels simple to human cognition does not correspond to what is simple, stable, or even possible under physical law. The persistence of the question reflects a mismatch between intuitions shaped by everyday environments and the behavior of reality at its most fundamental levels. Physics does not remove mystery by providing final answers to every question. It reshapes where mystery resides. As explanations deepen, some questions dissolve, while others emerge in their place. In this case, the mystery is not why something exists instead of nothing. It is why physical laws take the specific form they do, and whether those laws could have been otherwise. That shift does not close inquiry. It redirects it. Within modern physics, nothing has no operational definition. There is no experiment that produces it. There is no equation that describes it. There is no theoretical framework in which it remains stable or well-defined. Every attempt to formalize nothingness introduces physical content. Fields persist. Constraints appear. Rules govern behavior. What was intended as absence becomes a structured state subject to law. This outcome is not accidental. Physics is built on quantities that can be measured, modeled, and tested. A state defined by the absence of all structure cannot be incorporated into this framework without contradiction. This does not mean that physics explains everything. It does not claim to account for why laws exist or why reality takes its specific form. What it does show is more limited, but more precise. Physics does not require absolute nothingness to explain anything it observes. The universe, as far as current theory and measurement are concerned, is described entirely in terms of physical states and transitions between them. The concept of nothing plays no necessary role in that description. This analysis began with a contradiction. Regions defined as empty space do not behave as though they are empty. From that starting point, the investigation followed how science has repeatedly revised the meaning of nothing. In philosophy, it was treated as absence. In classical physics, it became an inert background. Relativity replaced that background with space-time geometry. Quantum theory went further, revealing unavoidable structure and activity, even in the lowest possible energy states. At no stage did deeper understanding preserve the idea of absolute emptiness. Each advance replaced it with physical constraints, mathematical rules, and measurable effects. Taken together, these developments lead to a clear conclusion. The universe, as described by modern physics, does not emerge from nothing. It evolves from conditions that are already physical, governed by laws that operate even in the absence of matter and radiation. The question of origins, therefore, is not resolved by identifying a moment of creation from absence. It is reframed as a problem of understanding how physical regimes transition, persist, and give rise to the structures observed today. The implications of redefining nothing are not confined to cosmology. They extend across multiple disciplines, reshaping how reality itself is framed and explained. In philosophy, these developments challenge traditional arguments about contingency. Many classical arguments assume that existence requires explanation, because non-existence is simpler or more natural. If absolute nothingness is not a physically meaningful possibility, that assumption no longer holds. The contrast between something and nothing loses its explanatory force. In physics, the disappearance of nothing motivates unification efforts. The tension between quantum field theory, general relativity, and cosmological observation is not peripheral. It highlights the need for frameworks that remain coherent across scales, from vacuum fluctuations to cosmic expansion. Questions about empty space become questions about the foundations of physical law. In epistemology, this shift forces a reassessment of what counts as explanation. Science does not begin from assumptions of absence. It begins from observable structure and consistent rules. By clarifying what nothing is not, modern physics sharpens the boundary between empirical explanation and intuitive assumption. Understanding the limits of nothingness therefore clarifies the nature of scientific inquiry itself. It reveals that explanation in physics does not rest on identifying a moment of creation from absence, but on describing how systems behave, transition, and persist under well-defined laws. The redefinition of nothing does not represent an isolated disruption. It follows a pattern that has repeated throughout the history of science. Again and again, scientific progress has required abandoning intuitively compelling assumptions. Earth was not the center of the cosmos. Time was not universal or absolute. Space was not a passive stage on which events merely unfolded. Each revision replaced familiar intuition with descriptions grounded in mathematical structure and empirical observation. In every case, the shift was not driven by philosophical preference. It was forced by evidence. Observations accumulated that intuition could not accommodate, and theories were revised accordingly. The disappearance of absolute nothingness follows the same trajectory. What once seemed obvious, that emptiness is simple, passive, and foundational, fails under closer examination. As with earlier revolutions, the role of intuition diminishes as the role of formal consistency and measurement expands. This pattern reveals something fundamental about scientific understanding. Progress does not come from refining intuition. It comes from identifying where intuition fails and replacing it with frameworks that better reflect how physical reality behaves. The loss of nothing as a meaningful physical concept is therefore not an anomaly. It is a continuation of a long-standing intellectual shift, one in which the universe becomes less aligned with common sense, but more accurately described. Human intuition did not evolve to understand fundamental physics. It evolved to navigate environments where space appears empty, objects appear solid, and time flows uniformly. At everyday scales, these assumptions work remarkably well. They allow reliable prediction and survival, but they are shaped by conditions far removed from those described by quantum fields, curved space-time, or emergent causality. Quantum phenomena operate at scales and energies that intuition never encountered during human evolution. Space-time curvature becomes relevant only under extreme mass and energy densities. Causal relationships lose their classical meaning when time itself is no longer fundamental. When these regimes are approached, intuition stops being a guide and becomes a source of error. The persistent appeal of nothing as a starting point reflects this mismatch. It feels natural to assume that absence precedes existence, that emptiness is simpler than structure, and that causes must always come before effects. These assumptions are cognitively efficient, but they are not physically required. Modern cosmology does not confirm intuition. It tests it. Repeatedly, the results show that the universe does not behave in ways that align with common sense. Empty space is not empty. Time is not universal. Causality is not absolute. The expectation of nothingness as a default state is a cognitive bias, not a feature of physical reality. Recognizing this does not diminish human understanding. It clarifies its limits. Intuition remains indispensable at human scales, but at the deepest levels of reality, it must be replaced by mathematical consistency and empirical constraint. The redefinition of nothing carries consequences that extend beyond cosmology. It forces a reassessment of what scientific explanation is designed to do and what it is not. Science does not explain why the laws of physics exist. It explains what follows if they do. Its strength lies in identifying consistent patterns, formulating testable models, and determining the consequences of those models under specified conditions. When absolute nothingness is treated as a non-physical concept, the demand for an external explanation of the universe takes on a different status. If there is no physically meaningful state of complete absence, then the universe may not require an explanation in the classical sense of emergence from nothing. This does not resolve every philosophical question. It does not claim that all aspects of existence are fully explained. Instead, it reshapes the boundary of meaningful inquiry within a scientific framework. Questions about origins shift from asking why something exists at all to asking how physical laws operate, where their limits lie, and under what conditions familiar concepts, such as time, causality, and space-time, remain valid. In this sense, the contribution of modern cosmology is not the elimination of mystery, but the refinement of it. Science narrows the range of coherent questions, distinguishing between those that can be addressed empirically and those that lie outside the scope of physical explanation. Even if the Big Bang is reinterpreted as a transition rather than a singular origin, one fundamental issue remains unresolved. Vacuum energy appears to play a direct role in cosmic expansion. In the simplest models, the accelerated expansion of the universe can be described by a cosmological constant, an energy density associated with empty space itself. Here, a severe discrepancy emerges. Quantum field theory predicts vacuum energy values that are vastly larger than what is inferred from observations of cosmic acceleration. The difference is not marginal. It spans many orders of magnitude, far exceeding the typical uncertainties encountered in physical theory. This mismatch is known as the cosmological constant problem. Its significance lies not only in its size, but in what it implies. Either our understanding of vacuum energy is fundamentally incomplete, or there exist physical mechanisms that dramatically suppress its gravitational influence on large scales. Both possibilities point to the same conclusion. The physical properties of empty space are not yet fully understood, despite their central role in shaping the evolution of the universe. The cosmological constant problem, therefore, occupies a unique position in modern physics. It sits at the intersection of quantum field theory, general relativity, and cosmology, highlighting a deep inconsistency between otherwise successful frameworks. Far from being a technical detail, this problem underscores a recurring theme. Empty space is neither simple nor inert. It is a dominant factor in cosmic behavior, and one of the least understood elements in fundamental physics. Once space-time itself is no longer treated as fundamental, the status of the Big Bang must be reconsidered. Several approaches to quantum gravity replace the classical Big Bang singularity with a transition between physical regimes. In these models, the universe does not originate from a point of infinite density. Instead, it evolves through a phase change, such as a bounce from an earlier contracting state into the expanding universe observed today. In this framework, the Big Bang does not mark the beginning of existence. It marks a boundary between regimes in which different physical descriptions apply. These scenarios do not assert that a specific pre-Big Bang history has been established. They remain theoretical and are not yet supported by direct experimental evidence. Their significance lies elsewhere. They demonstrate that consistent, mathematically coherent alternatives to a singular origin exist within the scope of known physics. A universe with a prior phase is not forbidden by physical law. It is permitted by models that resolve the breakdown of classical space-time. The critical implication is not which model is correct. It is that none of these frameworks require a transition from absolute nothingness. In every case, what precedes the Big Bang, if the term precedes remains meaningful, is a physical regime governed by rules, not an absence of reality. The disappearance of nothing from these models is not incidental. It reflects a broader shift in how fundamental physics treats origins, not as creation from nothing, but as transformation between physical states. If time and causality lose their classical meaning at the deepest levels, then the framework used to describe space-time itself must also be reconsidered. This is the point at which quantum gravity becomes unavoidable. General relativity provides an extraordinarily accurate description of space-time across a vast range of conditions. However, when pushed to the extremes implied by the earliest stages of the universe or the interior of black holes, its predictions cease to be physically meaningful. The failure is not subtle, it is explicit. When extrapolated beyond its domain of validity, general relativity predicts singularities, regions where space-time curvature, energy density, and gravitational strength become infinite. These infinities do not correspond to physical objects or events. They indicate that the theory is being applied in a regime where its assumptions no longer hold. General relativity treats space-time as a smooth, continuous structure. At sufficiently small scales, this assumption breaks down. Quantum effects can no longer be neglected, and the mathematical framework begins to produce results that cannot be interpreted physically. Singularities therefore mark the limits of approximation. They signal where a classical description of space-time must give way to a more fundamental theory. Several theoretical frameworks attempt to resolve this breakdown by incorporating quantum principles into the structure of space-time itself. Loop quantum gravity proposes that space-time is not continuous, but composed of discrete elements at the smallest scales. In this view, geometry is quantized, and classical space-time emerges only as an approximation. String theory takes a different approach. It replaces point-like particles with extended objects, altering high-energy behavior and smoothing out the divergences that arise in conventional quantum field theories. space-time geometry becomes one aspect of a broader mathematical structure: causal dynamical triangulations. Model space-time as an emergent entity constructed from simpler building blocks. Rather than assuming geometry from the outset, space-time properties arise statistically from underlying dynamics. While these approaches differ in method and interpretation, they share a critical implication. Space-time itself is not fundamental. It emerges from deeper degrees of freedom that do not resemble classical space or time. Quantum gravity, in this sense, is not a speculative addition to cosmology. It is a response to a precise failure point in existing theories. Wherever classical space-time ceases to be reliable, a quantum description becomes necessary. Once the idea of a classical beginning is set aside, a deeper implication follows. Time itself may not be a fundamental feature of reality. In general relativity, time is treated as a component of space-time geometry. It is dynamic, relative, and influenced by mass and energy. In quantum mechanics, by contrast, time plays a very different role. It appears as an external parameter, not as an operator subject to quantum uncertainty. These two treatments are mathematically incompatible when pushed to extreme conditions, such as those associated with the earliest stages of the universe. This incompatibility is not a minor technical issue. It signals that at sufficiently high energies, the concept of time used in everyday physics may cease to apply. Many approaches to quantum gravity take this seriously. Rather than assuming time exists at all scales, they suggest that it emerges from more fundamental, non-temporal degrees of freedom. In these frameworks, temporal ordering appears only after certain physical conditions are met. If this view is correct, then the question of what happened before the universe becomes conceptually misplaced. Without time, there is no meaningful sense in which one state precedes another. Under this interpretation, the universe did not emerge within time. Time emerged as part of the universe's physical description. The notion of a beginning, defined as a moment in time, gives way to a transition between regimes in which time itself becomes a valid concept. Taken together, vacuum energy, inflation, and quantum instability undermine one of the most persistent assumptions in classical reasoning, that the universe began with a clean, absolute origin. In everyday logic, a beginning implies a transition from non-existence to existence. It assumes a prior state in which nothing was present, followed by a moment in which something appeared. Modern cosmology does not describe such a transition. Instead, it describes transitions between physical regimes. Each regime is governed by a set of effective laws that apply only within a certain range of conditions. When those conditions are exceeded, the laws cease to provide reliable descriptions. Within this framework, the Big Bang is not treated as a creation event. It marks a boundary beyond which current theoretical models, particularly general relativity, can no longer be extrapolated with confidence. This distinction is essential. A boundary in description reflects the limits of a model, not necessarily the limits of reality itself. Conflating the two leads to the mistaken conclusion that the universe emerged from nothing, when the evidence instead points to a breakdown in our ability to describe earlier physical states. The collapse of the classical beginning does not eliminate the question of origins. It reframes it, shifting attention away from the idea of creation ex nihilo and toward the deeper problem of how physical laws operate and fail under extreme conditions. Classical causality rests on a simple assumption: causes precede effects in time. Events are ordered, and explanations trace backward along that temporal sequence. If time itself is emergent rather than fundamental, this assumption no longer holds universally. In frameworks where space-time becomes well-defined only after certain physical conditions are met, causal relationships cannot exist in their familiar form at the most fundamental level. Causality, like time, would arise only within regimes where space-time structure is stable enough to support temporal ordering. This reframes the question of origins in a significant way. Instead of asking what caused the universe, physics is led to ask what conditions allow causal structure to exist at all. Under this view, the search for an external cause assumes that causality applies beyond the domain in which it is defined. That assumption may reflect a limitation of human intuition, shaped by macroscopic experience, rather than a feature of fundamental reality. Causality does not disappear. It becomes contextual. It applies within the universe once space-time and time are meaningful. But it cannot be assumed to govern the conditions under which space-time itself emerges. The investigation of cosmic origins does not end with certainty. It ends with a clearer understanding of where certainty is no longer possible. Modern physics does not support the idea that the universe emerged from nothing. Instead, it points to a framework in which physical rules operate, even in the absence of matter, light, or classical time. What the universe appears to emerge from is not emptiness, but from rules that do not permit absolute nothingness to exist. Whether those rules are necessary, contingent, or themselves emergent remains unknown. That question lies beyond what current theory and observation can resolve. This uncertainty is not a failure of explanation. It defines the present boundary of understanding, a boundary shaped not by ignorance, but by what has been rigorously established. At that boundary, the question of origins does not disappear. It changes form, and for now, that change marks the furthest edge of what science can meaningfully say. If absolute nothingness is not a physically meaningful state, then the existence of the universe does not require explanation as an exception. Under this view, existence is not an anomaly that interrupts a default condition of absence. It is the natural outcome of physical law operating under conditions where absence itself is not permitted. The most accurate conclusion is therefore not that science has answered the question of cosmic origins. It is that science has identified a false premise embedded within the question itself. By removing the assumption that the universe emerged from nothing, modern physics reframes the problem of origins. What remains is not a mystery of creation from absence, but a deeper inquiry into the structure, limits, and implications of the laws that govern reality.